Hi, I'm Soumen Roy. First of all, I would like to say thank you to the organizer for selecting me for the presentation. Here, I will talk about the probing gravitational waves using the GNSS constellations. So I'm doing this project with Bruno and Justin in the Royal Observatory of Belgium and in Ussel, and in collaboration with AHIS and Diego Blas. So, so first of all, the detection of gravitational waves by LIGO-Fargo interferometers initiated a new era of astronomy. Also there is a detection by the for the of the stochastic gravitational wave background with pulsar timing errors in the nano-Hz range. The ground-based detectors and the planned future detectors like LISA, they all together can cover from milli-Hz to several kilohertz range. And this pulsar timing array can cover in the nano-Hz range. But there is a big gap around the microhertz range. Here, I'll show that how the GNSS constellation can cover that frequency band. So, so what is GNSS? Constellation. So those are basically the global navigation satellite system, and it refers to satellite system that provides geolocation and the time information and the navigation of the systems. So there are mainly four types of constellation of satellites. Their types depends on the country or region who operated them. So the GPS, which is operated by the US, and they have 31 operational satellites, and they are orbiting in the 6 orbital planes. The next one here, you see the Galileo that is operated by the European Union, and there are 27 the 27 operational satellites, and they are orbiting in the 3 orbital planes. And the third one is the GLONASS, that is by the Russia, and the Beidou operated by China. So these 4 different type of satellites, they not only have different orbital planes, they also have the different inclination angle, and they have also the different type of altitude. And this network of satellites could be very interesting for detecting the gravitational wave signal in the microhertz range. And we already have the 20 years of free archival in the orbital data, so we should take the advantage of that one. So before talking about this detecting the gravitational waves using the GNSS constellation, first of all, I will talk about how to the model the satellite orbit. So to model the satellite orbit, we generally define 6 Keplerian elements. So those are basically the semi-major axis, this A, and the eccentricity. And the third one is the inclination angle, that is basically the angle between the orbital plane and the equatorial plane. And the fourth one is the right accession of the ascending node. So this is basically the angle between the ascending node and the vernal equinox. And the fifth one is the argument of periapsis. So this is the angle between the ascending node and the direction of the perigee. And the sixth one, this is the true anomaly. So the true anomaly is basically the angle between the perigee direction and the satellite directions. So for a, when we talk about the gravitational waves, and which is basically perturbing the satellite orbit. So in general, we usually solve the Gauss planetary equations. So those are basically the 6 set of equations. Those are rely on the 6 parameter, and then we add the perturbative force, and then we solve, and then we see that how these parameters changes over time. So here I'll also show that how they are changing using this, how they are changing due to the gravitational wave signal. So we'll show here. So here, so there are, 2 cases what can happen, like the GW can cause the stretch the orbit, or it can squeeze it can stretch the orbit, or it can squeeze the orbit. So it depends whether the gravitational wave signal is out of phase or in phase. So when the gravitational wave signal is out of phase, then the orbit will squeeze. The orbit will squeeze, and if they are in phase, then the orbit will be stretched. And the most interesting phenomenon is basically the resonance effect. So what we saw generally that when the gravitational frequency is the multiple of the satellite orbital frequency, then the perturbative effect would be extremely significant. So in order to understand that effect, so we perform a simulation, the numerical simulation using the polyastro package. So what we are assuming that there is a circular orbit, and we are we are having the gravitational signal. These are the continuous gravitational signal. So we are also assuming that the frequency of the gravitational signal is fixed. And this is circular orbit, and we are observing for 5 days. So what you see in this plot, like the changes in the semi-major axis as a function of the observation time. So these are different, the panel are basically correspond to different type of gravitational wave signal, but with different frequency. So here the gravitational wave frequency, equal to the satellite orbital frequency. Here we are see the secular drift in the semi-major axis. And here, this is three times of the satellite frequency. There you also the secular drift. So, but there are other harmonics where they are not sensitive. So, this behavior is mostly oscillatory. So there is no secular effect. So in this plot, what we see here, the changes in the semi-major axis, and then x-axis is the gravitational frequency. So for each gravitational frequency, we simulate them for assuming that the 5 days of observation. So what you see from this plot, that the third harmonic is the most dominant harmonic here. And this response is not only, depend on the gravitational frequency, but it also depends on so many other parameters like the sky position of the source, or the structure, the shape of the orbit, or the source parameters. So first I will I'll talk about the eccentric orbit. So the same, the same simulation, but with there is eccentricity in the satellite orbit. So this is basically the properties of the initial value of the satellite that has been taken from the snapshot of 2016, the 21st November. And what you see here, the similar type of plot, but this is with the y-axis is the changes in the semi-major, the semi-major axis, and x-axis is basically the observation time. So in circular case, what we saw that it is mostly dominant to the third harmonic, but what you see here that it's not, it is, sensitive to, many higher harmonic. So that means that the if you incorporate eccentricity in the satellite, then they can cover the broad range of the gravitational frequency. And here what you see the similar kind of plot as we saw earlier, like x-axis is the gravitational frequency and y-axis is the changes in the semi-major axis. And what you see here that this changes, the secular drift for for different higher harmonics. So now let's focus on how this can change due to the sky position of the source. So again, this is with the continuous gravitational wave signal, but these four different plots are for the for different frequency of the gravitational wave signals. So this is with the same as the gravitational, the satellite frequency, and this is 2 times of the orbital frequency, and this is 3 times and 4 times of the satellite orbital frequency. So what you see that just because of changes in the gravitational waves, so the response is also changes. And this response, what you see that the red one is basically correspond to the positive changes in the semi-major axis, and this is the blue one is the negative changes in the semi-major axis. So there are, several sky position where the changes could be positive, and there are also the sky position where it could be negative, and it is sensitive to the position of the position on the sky. So now I'll show some one of the very interesting results. So here what we consider a network of satellites. So again, this is the snapshot for the Galileo satellites. So here we consider 4 satellites, and all of them are in the circular orbit, and they have the same semi-major axis, but the difference in the basically the longitude of ascending node and the true anomaly. So, and in this here, this is the snapshot, and this is basically their orbit, and this box is basically indicate the initial position. And here, what you see, like there are, I mean, the two cases, like this blue one and this orange one, the GSAT 102 and GSAT 203, they have the same orbit, but the difference is in the angular position. So here, what you see that the x-axis is the observation time. So we are here we consider for the 10 years of observation, and the y-axis is the secular drift in the semi-major axis. So what you see that, I mean, even though we are assuming a same gravitational wave signal, but the response to different satellites are significantly different from each other. So they have their own detection and they have their own, I mean, changes. So most, I mean, one interesting thing, like as I mentioned, like the GSAT 102, this is the blue one, and this orange one, the GSAT 203, they have the same orbit, but you can see that there is the changes in the semi-major axis is quite different just because of their the difference in the angular position. So this what it tells us. So this basically tells us that we can disentangle the effect of the gravitational waves using a network of satellites. Although, I mean, there could be I mean, the systematic effects or other effects. So just to mention, like, this is not the very first work. The similar type of work, like assuming the binary as a resonant detector, has been done with in the several cases in the earlier studies. So, for example, here we highlighted one of the studies by the Blas and Jenkins, and they have done this very recently. So what they did, like they assumed that the binary system in a stochastic gravitational background, and then they drawn a forecast on different type of binaries, and then how they are, I mean, at what frequency range or how much they are sensitive to detect the stochastic gravitational wave signal. Here, what you see, the x-axis is the frequency, and y-axis is the density of the stochastic background. And with this forecast, they compared with the existing detector like LIGO Fargo, and also compared with the LISA. So what you see here, that our GNSS can cover in this region. So this is basically between the microhertz and the milli-Hz. So where the LISA is not, I mean, sensitive enough. Okay, so there we can cover this gap. So this is very interesting, but there is a, I mean, as we know that our satellites is not free from the systematic effects. So there are several systematic effects. So for example, I mean, there are mostly, I mean, there are also perturbative forces, and there are mostly two types of systematic effects. So one is known as the gravitational systematic effects, and the other one is mostly known as the non-gravitational systematic effects. So for example, in the gravitational system effect, one of the effect is basically the Earth oblateness. As we know that our Earth is not the exact sphere, and this Earth oblateness actually changes our satellites. I mean, it for example, this oblateness changes the longitude of ascending node is basically decreasing 10 degree per year. So this is a very significant effect. But what we can do, like, I mean, we can model them very well as well. Okay, so here, I mean, I am also showing the other systematic effects, like due to the sun-moon tides or inhomogeneous Earth gravitational potential. And the non-gravitational systematic effects are basically the solar pressure radiation, or, for example, the Earth albedo or antenna thrust. So here, in this plot, what we are showing here, like the amplitude of the systematic effects. So for now, like, we can just focus on this middle one. So just to keep in mind that the lowest in the amplitude, I mean, in this plot, is basically connected to the highest value of the systematic effect. So because here the y-axis is in the negative power of 10. So our Galileo satellites are mostly affected by the Earth's non-spherical gravity, but at the same time, we can model them very well. And the second, I mean, the dominant effect are basically the geopotential that we can also model very well. But I mean, the only problematic thing is the solar pressure. I mean, we can model them, but they are not extremely, I mean, the reliable model. So you have to deal with them. So right now we are incorporating these systematic effects in our boxing model to extract the effect of the gravitational wave signal using the GNSS constellation data. And the most important thing we should note here, like none of this systematic effect can mimic the effect that we just discussed with a network of detectors. So this is very interesting, like using this network of satellites. I mean, one can actually so this motivates basically further work to develop the binary resonance into to develop precision tool for the gravitational wave astronomy. So now I'll come to the conclusion. So we have discussed about the drift in the semi-major axis accumulates over time due to the gravitational wave signal. And there is also the resonance effect that we saw that happens at several harmonics. And then we can disentangle the effect of the gravitational waves with a network of satellites. And the one of the interesting thing what we showed there, that even if there is the same orbit, but just because of different position, the effect also alter. So it's very sensitive to the properties of the gravitational wave signal. So that will basically help us to extract the the effect of the gravitational wave signal in the orbital data. And finally, our GNSS can cover the gap between the microhertz to milli-Hz. So that's all. Thank you so much for listening my talk.